Okay, welcome to session 8, I believe. First things first, I'll just clear out some terminology. So when we say h of z, right, what are we referring to? We are referring to the transfer function. Okay, and when we say h of n, then it's impulse response or your system response. Okay, so how are h of n and h of z related? H of z is just the z transform of our h of n, right? Okay, this is also represented with a double-ended arrow, that h of n in z domain is h of z, and when you take the inverse of h of z, you get h of n. Alright, so just be clear what the question is asking you. Is it asking for the impulse response or the transfer function? Alright, and similar for continuous. So in case of Laplace, h of s is our transfer function, and h of t is our impulse response. Right, and then h of t is related to h of s. Alright, so don't be confused with the terminology. Okay, next thing is I'll just cover some of the properties of Z transform, the important ones. 1 second. So there is standard scalar multiplication property. What does it state is, if I have a function x of n and I multiply it with a scalar a, then the Z transform will be x of z times a. Okay, scalar is just a multiplication, scalar stays the way it is. Alright, then we have right shift. What is right shift also equivalent to when you shift a signal to right? Time delay, correct. So right shift or time delay. Okay, so the general properties of this form, so this x of n minus m u of n, so x of n is right shifted by m. Okay, so the general property gives us a Z transform of 1 over z raised to power m x of z plus 1 over z raised to power m again, n equal to 1 to m x of minus n z raised to power. Okay, so whenever you have a time shift, time delay with m, you'll have z raised to power minus m multiplied with your Z transform. Okay, and these are referring to your initial conditions. Alright, so let's just see a few examples. So we have x of n minus 1 u of n. What will be its Z transform? 1 of z, x of z plus, okay, let me write it here, 1 over z summation n equal to 1 to 1 x of minus 1. Yeah, because the n is just from 1 to 1, and this is z. This z and this z cancel, you get z raised to minus 1 x of z plus x of minus 1. Okay.
And do we also have this time? Do we need to compute every time the
what?
I'm sorry, no. I see it.
Okay. All right. Got this. So let's do another one. So if we have, you didn't get it. Sorry. Okay, so don't forget these initial conditions. Just don't write this term and be done with it. Okay, check if you have initial conditions or if it's given that the initial conditions are 0.
Oh, this is in discrete, right?
Yeah, everything is discrete.
No, it's in
So,
discrete, right?
but the initial conditions, they need to be given to us. Like we cannot find them otherwise.
No. So it's either given to you in the question or it's given to you in the question that initial conditions are 0. If in the worst case nothing is given to you, write it that you assume that the initial conditions are 0.
Okay.
But that shouldn't be the case at any point of time. Alright? Okay, another quick example, xn minus 2 u of n. Okay, tell me what to write. Oops, sorry. 1 over z square.
Z, x to z.
X of z.
Plus 1 over z square.
Plus 1 over z square.
N equals to 0 to 1 to 2.
2.
X to the minus 2. To the power minus.
X of, you'll write minus n now because you have 2 values of n. I wrote x of minus 1 previously because there was only one value. Okay? Right? So z to the power n. Okay?
You can expand that, right?
Yeah, I'll just do that.
Okay.
So plus 1 over z square. First term will be x minus 1 z plus x minus 2 z square. Right? Finally, I get x z raised to minus 2 x of z plus 1 over z x minus 1 plus x minus 2.
So there, x of z is whatever x of what the transformation of x without the delay.
Yes.
So we ignore the delay and we plug it in there.
Yes. So this is the transformation of x of n. Simple.
Okay.
Okay? Alright. Now, similar, we have a left shift property which is also called time. Advance or delay? Advance. Good. Okay. So in this case, our function will be in the form of x of n plus m u of n, which will have a transformation of the form z raised to power m x of z minus z raised to power m n equals to 0 to m minus 1 x of n z raised to power minus n.
So it's 0 to m minus 1 now?
Yeah, it's 0 to m minus 1 here, and that's 1 to m in the other case. Alright, so let's just do quick example. Let's go with x of n plus 2 u of n. Okay, so m is 2 here, so you'll have z square x of z minus z square summation n equal to 0 to 1 x of n z raised to power minus n. This translates to z square multiplied with x of 0 plus x of 1 z. Wait a second.
X of z minus 1 because we have negative there.
Oh, sorry. Yeah. So this is over z and this is over z. Okay. Alright, so then we'll have z square x of z minus z square x0 minus zx1. Alright? Okay. So this is done. Then we have, again, like we had in Laplace, that convolution turned into multiplication in S domain. Similarly, if we have time convolution, right? So let's say x1n is convolved with x2n. In Z domain, this will become x1z is multiplied with x2z. Alright? So whenever you do your transformation, convolution becomes multiplication. Okay? Okay, so that's the major properties that we have. Next, I'll just do an example quickly. Solving difference equations. I think this was done in class. I'm not entirely sure. Okay, so the difference equation that we have is y of n plus 2 minus 5yn plus 1 plus 6yn is equals to 3x of n plus 1 plus 5x of n. Alright, and initial conditions are given to us. That is y minus 1 is equals to 11 over 6, y minus 2 is equals to 37 over 36, and x of n is equals to 2 raised to power minus n u of n. Alright? Okay.
I have a question.
Yes.
Over there, the x of n already has the u of n. But
yes.
in the formulas, we get the transformation of xn times u of n already. So do we ignore the other u? Because we would have x of n, u of n times u of n. But you see the formulas you had on the previous page?
Yeah.
They like the template says x of n times u of n transforms.
Yeah, so u of n is just showing you that it's causal, nothing else.
Oh,
okay. Okay? You don't touch u of n.
Okay.
Okay? So u of n over here also, it's only showing you that it's causal.
Okay.
Right? It's only starting at 0 and everything before 0 is 0. Okay?
Yes.
So you don't take its z transform. Okay? So okay. So first step, we can write, either take the z transform directly from here or transform this equation to y of n minus 5y n minus 1 plus 6y n minus 2, because these conditions are given to us. Okay? For this operation, we'll need 0, 1 and 2, which we don't have. Right? That's why we are delaying it by 2. Okay? So 3 of x n minus 1 plus 5x of n minus 2. Okay? So y of n, what is this z transform?
Y of z.
Correct. That was easy. Okay, y of n minus 1?
C to negative 1, y of c.
Correct.
Plus y of 0. Negative 1.
Correct. Okay. Y of n minus 2?
0 of negative 2, y of c.
Z of negative 2, y of z plus
z of negative 1,
z of negative 1.
y of negative 1.
Correct.
Plus y of negative.
Correct. Good. Okay. And for x of n, again remember that x of n is causal, so I'll just pull it down here. So, what will be its z transform?
X of c.
That's it?
No, c to negative 1.
Correct. Z to negative 1, x of z, and plus x minus 1, but this is 0. Alright? And similarly for x of n minus 2, we'll have z to the negative 2 x of z plus z x of minus 1 plus x of minus 2. Okay, and both of these are 0.
We need to do anything with the constants or not?
Yeah, the constants are just scalar multiplications, right? So 5 will stay here the way it is. Okay, so just combining all of this together, we'll have y of z minus 5, z inverse y of z, plus y of minus 1 is 11 over 6, right? Plus 6, z to the minus 2 y of z, plus z inverse 11 over 6 plus 37 over 36 is equals to 3 z to the negative 1 x of z plus 5 z to the negative 2 x of z. Just make sure these are square brackets. That's how we denote discrete time analysis. I never get square brackets correct for some reason. It just never comes out. Okay, so what is the next step? We'll just group the terms together now, right? So taking y of z common. Okay, so we'll have 1 minus 5 over z plus 6 over z square y of z, right, minus 3 minus 11 over z. This is just simplified from the constant. Okay, is equals to 3 over z minus 0.5. We've just substituted x of z here. Okay, plus 5 over z into z minus 0.5. All right, any questions? Okay, now let me write down what x of z is. X of z originally is z over z minus 0.5. Okay, that is just substituted. So from here the question could ask you to give a complete solution for y of z. Okay, so you'll just take this to the other side and take this in the denominator and you'll have your y of z. Okay, another question could be separate out 0 input and 0 state. Okay, so what is the 0 input here and what is the 0 state? 0 input is because of our initial conditions, correct? And which part of this equation is because of the initial conditions?
Right after the waves.
This one, correct? So this is our 0 input. Okay, and so 0 state is because of the input that you are applying, that is x of n. So which is the part that is because of x of n? Yeah, right. So this is the 0 state. Okay, so depending on the question, if the question asks you to give a complete solution, you don't care about this differentiation. Okay, if it's asked you to give 0 input and 0 state separately, then keep these two things separate in the following steps. Okay,
So x of z is always that value, or is given in the question?
no, it's given in the question, right? X of n is given to us, so we've just taken the z transform of this. Okay, so whatever is given to the in the question to you, you'll take the z transform of that. All right, now just to show what it looks like, so if it's a combined solution, let me say combined solution, right, that is 0 input plus 0 state, we are not separating them out. Okay, then y of z will look like something like this. Plus 6. Okay, next step, take this to the other side as a denominator and simplify your yz over z. Okay, follow this. Now simplify this using your partial fraction expansion. Right? Then your Heaviside method to find the constants. Right? And once you have that, you take this z to the other side. Take z to the RHS, the right hand side.
Can we be pretty safe thinking that we're always getting the extra z?
Yeah, it's not always guaranteed that you'll easily get the z out.
But what on the homework you just like divide the other side by C.
Yeah. So in this question, it's apparent that z is coming out. I mean, it's there. But in all the questions, it won't be. Okay? Okay. So this is the summary of the technique that you'll use. Again, you'll use the same technique. If you're asked to give 0 input and 0 state separate, you'll just keep those two terms separate in your computation. Okay? So in that case, your y of z will look like, one second, let me write it here, z square minus 5z plus 6, 3z minus 11 plus z 3z plus 5 over z minus 0.5. 0 input, 0 state. Okay, and then solve these two separately. Okay, so you can call this as y1z and y2z. Okay, take the denominator down and call it y1z and y2z and solve separately. Alright? So that is with the difference equation.
So which would be easier, like the simple equation, or that one's always easier?
The combined one?
Which one is like easier to do?
Depends on the question. It's not easy. So if the question is asking you to give a combined response, it's not asking you to give 0 input and 0 state separately. You just get the y of z value. If it's asking you to do it separately, you have to do it separately. Okay, so another example. Okay, so transfer function related example. Right, so this is example 5.7 from your textbook. Alright, okay, so difference equation that is given to you is y of n is equals to x of n minus 1, u of n minus 1. Alright, now to get the transfer function, the first step is to take the z transform. Okay, this is the only thing that's given to you in the question, nothing else is given. Okay, so if nothing else is given, assume that the initial conditions is 0. Okay, so taking the z transform, we'll get y of z is equals to 1 over z x of z. Alright, so my h of z is defined as y of z over x of z, the output response over input response. Oops, sorry. Right, which is given as 1 over z. So this is our ideal delay unit. In a lot of your signal processing and filtering classes, you'll come across this, the ideal delay unit.
1 over z, ideal delay.
Yeah. So what it means is you have an input x of n, u of n. You give it to a system, let's say h of n, h of z is its transform, okay? And your output is y of n, right? This is also represented as z raised to the power minus 1 directly, a lot of times.
And y of n is equal to x n minus 1?
Y of n is equals to x of n minus 1, u of n minus 1.
Also the ideal delay. Delay.
Because it delays. There are no initial conditions, it does not result in any unwanted responses. Okay, that's what's called an ideal delay. Okay, so in a lot of classes, it will be represented as directly 0 raised to the power minus 1. So whenever you're supposed to delay a signal, you just apply this delay unit. All right, and this is how you represent your systems also. So h of z is also defining our system. Okay. Okay. Next thing we'll talk about is stability. Should clear stuff up. All right. Okay. So h of z. So if our difference equation is of the form q of z, y of z is equals to p of z, x of z, right? So h of z is equals to yz over xz, which is equals to p of z over q of z. This is what we do mostly, right? Now, when we talk about the stability of a system, that is stability of h of z, something that Professor Hudge had pointed out in class, if q of z is our characteristic polynomial or characteristic equation, okay, then we can talk about its intrinsic stability. Only then, when q of z is our characteristic polynomial. Okay, otherwise we cannot talk about it. By intrinsic stability, I mean asymptotic stability. Okay. Now, when is q of z a characteristic polynomial? So this condition happens when p of z and q of z do not have a common factor, right? If they have a common factor, then my q of z, the denominator that I have, it does not represent my characteristic polynomial because it's missing that factor. P of z is cancelling a factor out. Okay? So, when this is the case when q of z is a characteristic polynomial. The other case is when q of z is not my characteristic polynomial. Right? In this case, I can only talk about extrinsic stability, which is also
extrinsic.
Yeah, extrinsic.
Oh.
Sorry, my handwriting is disgusting. Which is also called BIBO stability, which is bounded input, bounded output. So what will you look for extrinsic stability? You will just see that if it has the poles or the roots of the denominator q of z is inside the unit circle. Okay, so when we're in S domain, our poles had to be in the left hand plane. Okay, the left hand plane of S domain translates to the unit inside the area inside the unit circle in the Z domain. Okay, so in Z domain, for stability we need this area. Okay, this is my unit circle, real imaginary axis. Okay, so this is in Z domain. All right. So why is this the case? So when poles are within the unit circle, my h of n are decaying exponentials, and hence their sum will converge. Okay, that is my it will be less than infinity. Okay, all good? And for asymptotic stability, it's again the same case. So let me outline the cases for asymptotic stability. So QZ is our characteristic polynomial. All right. So one case is when all poles lie within unit circle, then it's stable. Okay. Second case is at least one pole is outside unit circle, or there are repeated poles on the unit circle. Okay, then it's unstable. All right, and third condition is marginally stable. So no poles outside the unit circle and non-repetitive poles on the unit circle. So it's marginally stable. Okay, all clear? Good. Okay.
What does
Number
number 3 mean?
3 means, okay, so
And what's the difference between number 3 and number 1?
So if you look at a system such as an oscillator, a cosine or a sine, it has its poles on the unit circle. It oscillates. It does not converge to something, right? That's why it's called marginally stable. It does not go to infinity also. It oscillates between 1 and -1 continuously, right? So it's bounded between those two values, 1 and -1, but does not converge to any one of them, right? That's what the meaning of marginally stable is. When it's absolutely stable, it converges to a single value. Okay? And when it's unstable, it goes to infinity. Okay. So from the exercise, I'm going to do another question, which is 5.15a. This is to help you with your homework. Okay, let me find the question. Found it. Okay, so simple question, you need to find the inverse Z transform. I think everyone is comfortable with this thing at least by now. Okay, so the Z transform that we have is Z multiplied with Z minus 4 over Z square minus 5Z plus 6. First step, factorize our denominator. What does it factorize to? Let me call this X of Z. Yeah, what? Minus 2 minus 3. And another thing that I've noticed a lot. Oh yeah, sorry. When you solve this, so you'll get Z is equals to 2 and Z is equals to 3, right? This translates to Z minus 2, Z minus 3 and not Z plus 2, Z plus 3. Okay? So don't make this mistake. What this means is Z minus 2 is equated to 0 and Z minus 3 is equated to 0. That's how you get Z equal to 2 and Z equal to 3. Okay? Just remember that. Don't make that mistake. Okay. So what is the next step? Is it?
Separate the Z.
Yes. So X is Z over Z. Alright? and we have z minus 4 over z minus 2, z minus 3. Also always check the degree, that the degree of a numerator is less than the denominator. If it's not, do your long division method. Okay? And you'll get a constant term from that. So after the partial fraction expansion, so then we go forward with partial fraction expansion, and you will get x of z over z is equals to 2 over z minus 2 minus 1 over z minus 3. Okay? And then what's the next step? Put the z back. So we'll have 2z over z minus 2 minus z over z minus 3. Anyone remembers why we put the z back? What is the point of doing this?
Not to get delay, I guess.
Correct. So if you don't put the z back, you'll get u of n minus 1 terms in your final answer. Okay, so do not have that. We divide by z and then multiply with z later. Alright, so what will our x of n look like? 2
2 to the n plus, oh, minus 3 to the n, and how about that is u,
u, not u to the n. Okay, that's your answer. Simple. So you can at least do 2 questions of your homework with this.
already done it.
Okay, already done. That's good. Okay, so another example that we're going to do is 5.3.7. Okay, it's again solving a difference equations. So let's do this. We have y of n plus 2 minus 2y of n plus 1 plus 2y of n is equals to x of n. Y of minus 1 is given to us to be 1, y of minus 2 is given to us to be 0, and x of n given to us to be u of n. Alright. Now, what is the first step? Correct. Okay. So first step is to delay. So you'll have y of n minus 2 of y of n minus 1 plus 2y of n is equals to x of n minus 2. Correct. Now we'll take the z transform. Correct. So you'll have y of z minus 2 plus the condition, this condition, plus 1, right? And 2 times, oops, this should be minus 2. You should correct me if I make those mistakes. Okay. So z raised to minus 2, y of z, again, correct. That's it, because this is 0. This condition is 0. Alright, and then just the z transform of u of n minus 2, which will we get to be 1 over z minus 1. Why? Because x of n has a z transform of z over z minus 1, correct? But here we are delaying it by 2, so this is divided by z square. So you have 1 over z square multiplied with z over z minus 1. Alright? And that's how you get this. Okay? And then we go forward in our standard method. So this only asks you to solve for y of n, right? It does not ask you for 0 input in 0 state. So you go all the way, combined solution. Okay? Now I'm just going to write y of z over z. I'm skipping a few steps. Okay, over z minus 1, z square minus 2z plus 2. Again, partial fraction expansion. Alright, and then we'll have y of z is equals to z over z minus 1 plus z into z minus 1 over z square minus 2z plus 2. Okay, and this again you'll use your table. So one important transform pair to remember is as follows. I'll just write it down for you. Okay, so important transform pair to remember is the 12C. Let me pull that up. No, not you.
So is that the one for? Is that the one for complex?
I mean the complexes add up and you get cosine. So one second, let me pull it up on the screen if I can find it. That was bad. This one. So our formula, the term that we get for yz is in terms of z multiplied, just follow the right hand side of 12c pair, z multiplied with z minus 1 over z square plus 2 z square minus 2z plus 2. So matching these values, you'll get your capital A, capital B, small a and mod gamma square, and then you just substitute back. Alright, and the transform table will be given to you, no worries, you don't have to remember this. Okay, another last quick example, I believe. Is 5.3.21. Okay, so it's asking you to find the zero state response with the transfer function. So the transfer function is given to you and x of n is given to you, right? We can easily find y of n. So how do you find that? X of n is given and h of z is given. Okay, we know that y of z is equals to h of z multiplied with x of z, right? All you have to do is take the z transform of x of n, get x of z, solve this and get your y of n. Okay, so let's just do this example. So we have x of n is equals to u of n given to us, and h of z is given to be 2z minus 1 over z square minus 1.6z plus 0.8. Okay, what is the transform of x of n? What is x of z?
1 over z.
X of z is 1 over z.
C over C minus 1.
Yeah.
No, Laplace 1 over s.
Very nice. Okay, so x of z is z over z minus 1. Just multiply the two. We'll have y of z, which is z times 2z minus 1 over z minus 1 z square minus 1.6z plus 0.8, right? Then we take yz over z and do the partial fraction expansion. Correct? Once we've done the partial fraction expansion, we have y of z is equals to 5 z over z minus 1 minus 5 z, and we take the z to the other side. Okay? Right? And then we have over z squared minus 1.6 z plus 0.8. Right? We know this inverse z transform of this thing. What is it? Correct. Good job. Finally. Okay. So this is again similar to the pair 12C in transform table. So capital A is 1, B is minus 1, A is minus 0.8, and mod gamma square is 0.8. Okay?
You go directly for the cosine without doing anything else. Cosine.
Yes. What is the point of giving you the transform table for the exam if you don't use it?
But it kind of looks like the type of thing we would do complex.
Why go the hard way if things are given to you easier?
I
Right? Okay, so this translates to, one second, I don't remember. So we'll find r and beta and theta. It's fine. So r is given to be, I have to go back to the table. Okay, so r is given to be under root capital A square gamma square. This will be pretty time consuming for you to find. Over mod gamma square minus A square. Okay, this is just r. Then you need to find beta, which is cos inverse of minus A over mod gamma. And then you find theta, which is tan inverse of A small a minus B over A under root mod gamma square minus A square. Okay. Once you found this, then your answer is r multiplied with mod gamma raised to power n cos gamma n plus theta u of n. Okay? So, in this case, the answer does not matter. You can find the answer. Okay? That's it for today. Thanks, Daniel.
Do you know if Fourier series are going to be testing Wednesday?
Fourier series testing Wednesday.
We don't test on Wednesday. Like
Yeah.
Monday?
The exam. The midterm is on 6th.
Yeah, August 3rd. So, do you know if Fourier series are going to be this time? Or we haven't had any homework?
Yeah, but none of the homework has Fourier series.
Yeah, this Friday homework has 0 Fourier series.
I'll ask the professor what his plan is. Usually I think that we do. Thanks, okay. What? Can I see the table?
I was sent to the online.
So it's got like a bunch of coordinates. So we